Now we extend the method of variation of parameters for solving non-homogeneous differential equation to the nth order non-homogeneous differential equation. For the differential equation, nth derivative of y plus p1x, n minus 1th derivative of y plus so on, plus pnx y is equal to rx. For this nth order linear non-homogeneous differential equation, we proceed the same way as we did for n equal to 2. Let the solution of the associated homogeneous differential equation be y is equal to c1y1 plus c2y2 plus so on plus cn yn. So here y1, y2 and yn, they are linearly independent solution of the associated homogeneous differential equation. So we take the candidate solution or the candidate for the particular solution to be y is equal to v1 y1 plus v2 y2 plus dot 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 plus vn yn. So v1 v2 vn are functions here. So we have replaced the constant c1 c2 cn by functions, and that's why this method is called variation of parameters. We have varied the constant c1 c2 cn by using functions. So we take y is equal to v1 y1 plus v2 y2 plus dot 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 plus vn yn as the candidate for particular solution, and we wish to determine what v1 v2 vn will work. For that we differentiate y. We get y prime is equal to v1 y1 prime plus dot 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 plus vn yn prime plus v1 dash y1 plus dot 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 plus vn prime yn. Now here we demand that the terms that appear here, namely v1 prime y1 plus dot 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 up to vn prime yn, this is equal to 0. Then y prime will be only the first n terms. Then we differentiate this y prime. So y double prime is equal to v1 y1 double prime plus dot 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 plus vn yn double prime plus v1 prime y1 prime plus dot 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 plus vn prime yn prime. So here only n terms was surviving for y prime, and when we differentiate we got 2n term for y double prime. Again we demand all these terms which contain y v prime, namely v1 prime, v2 prime up to vn prime, the sum of those terms we take it to be 0 like before. So this we take it to be 0. So again for y double prime we will have n terms. We continue this way. So we obtain n minus 1 derivative of y equal to v1 n minus 1 derivative of y1 plus dot 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 plus vn n minus 1 derivative of yn plus v1 prime n minus 2 derivative of y1 plus dot 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 plus vn prime n minus 2 derivative of yn. Here again we demand the sum of all those terms which contains v1 prime, v2 prime and vn prime, that to be equal to 0 as before. Then we differentiate the n minus 1 derivative of y to get the nth derivative of y, there will be two n terms here because in the n minus 1 derivative of y, there are n terms which are surviving after this assumption. So nth derivative of y is equal to v1 nth derivative of y1 plus dot 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 plus vn nth derivative of yn plus v1 prime n minus 1 derivative of y1 plus dot 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 plus vn prime n minus 1 derivative of yn. Now we substitute y, y prime and so on up to nth derivative of y in the non-homogeneous differential equation, just like we did for the second order non-homogeneous differential equation, and you use the fact that y1, y2 and yn are the solution of the homogeneous differential equation. So we get that y1 prime n minus 1 derivative of y1 plus dot 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 plus yn prime n minus 1 derivative of yn is equal to rx. This is similar simplification we had got for the second order case. So now we proceed by looking at the system of equations which involve v1 prime, v2 prime up to vn prime. We have n such equations. This is one equation. We have this equation here equal to 0, and we have this equation here, and we have this equation here. All these n equations we collect and form the matrix equation with respect to this. So here we treat v1 prime, v2 prime, vn prime, we treat them as variables, and the coefficient matrix here consists of entries y1, y2 up to yn in the first row, y1 prime, y2 prime up to yn prime in the second row, and so on in the last row. N minus 1 derivative of y1, n minus 1 derivative of y2, n minus 1 derivative of yn. This when multiplied to this column matrix consisting of v1 prime, v2 prime up to vn prime, we get 0, 0, 0 rx. These are precisely the equation. This one, this one, this one, this one, and the other ones which are indicated by these dots. So the n many equations, so they form this matrix equation. So we solve for these variables using Cramer's rule, and once you get the values of v1 dash, v2 dash to vn dash, means the expression of these functions, then we integrate each of them to get v1, v2 up to vn. We did the same thing for second order ODEs, and once we have this expression for v1, v2 and vn, we substitute it in the starting equation, that is y is equal to v1 y1 plus v2 y2 plus dot 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 plus vn yn. This is the way we will get a particular solution using variation of parameter for the non-homogeneous ODE of nth order. Here is an example. So we want to solve third derivative of y minus second derivative of y minus first derivative of y plus y is equal to rx. first we look at the homogeneous ODE associated to this, and that homogeneous ODE has the following characteristic polynomial: m cube minus m square minus m plus 1, which we can factorize as m minus 1 whole square multiplied by bracket m plus 1 bracket close. So looking at the zeros of this polynomial, we form this basis of solution. Namely, here 1 is a repeated 0 of this polynomial. So we have ex corresponding to this and x ex because of the repetition. And we have minus 1 as a 0 of this polynomial with multiplicity 1. So we write e raised to minus x as one of the solution of the homogeneous ODE. So this is the basis of solution of the homogeneous ODE. Now with this basis of solution, we calculate the Won's gain. We use Abel's formula. It says the Won's gain Wx is equal to W evaluated at 0 times e raised to minus integration from 0 to x p1 t dt. Here p1 is minus 1, so we have this equal to w0 e raised to integration 0 to x dt. So that is equal to w0 times e raised to x. Now we'll calculate what is w0. For that, we first write down the expression for wx, the Won's gain. So first comes in the first row this y1, y2 and y3. So we have ex, x, ex and e raised to minus x. Then their derivatives come here and their double derivatives come here. This is the expression for Won's gain. Now we want to calculate Won's gain at 0, w0. So w0 is equal to the determinant of this particular 3 cross 3 matrix. So you have to substitute 0 for x here. So e raised to 0 will be 1, and here 0 times e raised to 0. So this is 0 and so on. So on putting 0 for x in this determinant, we get this determinant, we evaluate this determinant, and the value comes out to be 4. So this tells us that the Won's gain is equal to 4 times e raised to x. So we write that 4 here, and so we get wx is equal to 4 times e raised to x. We are interested in computing this determinant. This determinant, we call it w1x, that is equal to the 3 cross 3 matrix that obtained by replacing the first column of our Won's gain determinant matrix by 0 0 rx, and then we calculate the determinant of this. So we get minus rx times bracket 2x plus 1. When you multiply this, you get this. Why did we calculate w1x? Because in Cramer's rule, when you want to calculate v1 prime, its expression is given by w1x divided by wx. Look at this. So when you want to use Cramer's rule to compute v1 prime, that will be equal to the w1x in the numerator divided by the w at x, that is the Won's gain. It is coming from this matrix. Determinant of this matrix is the Won's gain. So we got W1x. Similarly, we can calculate W2x and W3x. We obtain W2 by replacing in this Wx the second column by 00Rx and leaving the rest of the entries as it is and computing its determinant. And we compute W3x by replacing the third column here by 00Rx and keeping the other entries as it is and computing the determinant. So when you do this computation, we get W2x to be equal to 2Rx and W3x to be equal to Rx e raised to 2x. So from this we can compute what is V1 prime, V2 prime and V3 prime. V1 prime is W1x divided by Wx. V2 prime is W2x divided by Wx and V3 prime is W3x divided by Wx. And so V1, V2, V3 are given by their integration. So we replace in the expression of Yx is equal to V1 Y1 plus V2 Y2 plus V3 Y3, the values of V1, V2 and V3 that we obtained here. So this is the expression we get. So Yx is equal to, this is our Y1 and this is the V1 that we obtained, because in numerator this thing is there and in the denominator is the own scan, this quantity, and then its integration. Similarly here, this quantity is Y2 and this is W1 by W and its integration. So this is the V2 plus here we have Y3 and this is the V3, because V3 prime was equal to W3 divided by W, that is written here. So this is the solution using variation of parameters.